So this short video is a recap on vector spaces. So vector spaces are a concept you should be familiar with from your undergraduate studies, but they're going to be an important concept throughout the module, and so I want to just tell you the key points about them that we'll rely upon. So the way we think about vector spaces is that a vector space, V, is a set of objects or vectors. These are our objects. So let's write it as V. It's going to be just a collection of objects, V1, V2, etc. So it's a set of vectors V such that if U and V are in the vector space, okay, so capital V for the vector space, then U plus V is in the vector space. And so that's the first point. The second point is if U is in the vector space and lambda is a real number, we're going to be considering real vector spaces here, then lambda times U is in the vector space. Add and multiply here obey all the normal rules. So U plus V equals V plus U, and lambda times U plus V is lambda U plus lambda V, etc. So the examples we normally think of are Euclidean space, things like R3. Okay, so that's the kind of thing to hold in mind. Think about vectors in three-dimensional space. Now there are a few important concepts we'll need. The first of which is the concept of a subspace. So we say that U, a subset of V, is a vector subspace of V if U is also a vector space. Okay, so vector space, a vector subspace is just a subset of vectors which is a vector space in its own right. We'll have some examples of this in a minute. One of the concepts we're going to need is the concept of a basis of a vector space. And in order to define what a basis is, we first need to define what linearly dependent and linearly independent means. So first of all, we say that a set of vectors V1 up to Vn, say, are linearly dependent if we can write one of the vectors in terms of the others. So if there exists lambda 1 up to lambda m minus 1, say, real numbers, such that Vn can be written as lambda 1 times V1 up to plus lambda 2 times V2 up to lambda n minus 1 times Vn minus 1. So that's linearly dependent. We say V1 up to Vn are linearly independent if we can't do this. If there is no set of scalars which allow us to write one of the vectors in terms of the others. Okay, so the way we write this is we say V1 to Vn are linearly independent if lambda 1 V1 plus lambda 2 V2 up to plus lambda n Vn equals 0, and if whenever that is true, that implies that lambda 1 equals lambda 2 equals lambda n equals 0. Okay. So in other words, there's no combination of scalars that allow us to write any of the vectors in terms of any of the other vectors. The final concept we need before defining a basis is the concept of a span. Span of a set of vectors v1 up to vn is just a set of all linear combinations of these vectors. So what are the linear combinations? Well, let's write it out. So we say the span of v1 up to vn is the set of vectors that is the sum lambda 1, or let's say lambda I vi, okay, and we're going to sum from I equals 1 up to n, okay, such that the lambda i's are real numbers. Okay, so we multiply all the vectors by a number and then add them up. That is the span, the set of all linear combinations. So finally, this leads us to the concept of a basis. So let's say a basis for vector space V is a set of linearly independent vectors. Let's say v1 up to vn that span V. So in other words, the span of v1 up to vn is V. And because they're linearly independent, we know that we can't make one of the vectors by a combination of all the others. So if we remove an element from our basis, we reduce the size of the space. So the final thing we need is dimension. Okay, we say the dimension of V is the number of vectors in the basis. In any basis for V. Okay, so let's have some examples. So let's think first of all about R3. Okay, so let's just list some vectors. So let V be R3. So let's write down some vectors. Let's have 1, 0, 0, 1, 1, 0, and 0, 1, 0. Well, are these vectors linearly independent? Let's call them v1, v2, and v3. No, they're not linearly independent because we can make v2 by adding up v1 and v3. Okay, so these are linearly dependent. What's the span of these vectors? Well, the span of these vectors is the same as the span of v1 and v3, because we can make v2 by linear combinations of v1 and v3. Okay, so by removing v2 doesn't change the span. Okay. Let's call this U. Okay. U is a subspace, a vector subspace of V. It's a two-dimensional plane. R3. So let's think of a basis now. Well, the standard basis which we'll use for Euclidean space we often write as E1, which is 1, 0, 0, E2, which is 0, 1, 0, and E3, which is 0, 0, 1. So note that these three vectors are linearly independent. I can't make any one of them by a combination of the other two. And so, and at the same time, the span of E1, E2, E3 is obviously the whole of R3. So we must have the dimension of the vector space R3 is 3. What about U? What about our subspace U? U was the span of 1, 0, 0, 0, 1, 0. Okay. And we know that 1, 0, 0 and 0, 1, 0 are linearly independent. So we must have that the vectors 1, 0, 0 and 0, 1, 0 are a basis for U. So that's two vectors in the basis, so we must have that the dimension of U is 2. One thing to note is that bases are not unique. So we also have that U is the span of 1, 0, 0 and 1, 1, 0. Okay. Those two vectors also can create any point in U. So an alternative basis is 1, 0, 0 and 1, 1, 0. And they're both bases for U. Okay. But of course, any alternative basis must have the same number of vectors in, because that's the dimension of the space, and it's fundamental to the space. So here are 3 tasks for you. So the first task is to think about, are the vectors 2, 1, 1, 1 and -1, 2, so these are all vectors in R2, so are these linearly independent? Okay. The next question is, give 2 different bases for all R2. So bases is the plural of basis. Okay, so 2 different bases for R2. And the third question is, say, write 3 different subspaces of R3. Okay. So as I say, this is all material that you should be familiar with. This is just a recap that hopefully puts the key concepts back in your mind. I'm going to rely on these concepts throughout the module.